Hello everyone, I'm Maki Ogawa from the University of Tokyo. Today I will present our research, Effects of Proprioceptive Attenuation with Noisy Tendon Electrical Stimulation on Adaptation to Beyond Real Interaction. As a background of our research, Beyond Real Interaction, or BRI, refers to interactions in virtual reality that transcend physical constraints. It offers effective user experiences such as expanding the manipulation area with an extended arm and duplicating or replacing body part movements. However, one challenge of BRI is that it requires users to adapt to novel sensory motor mappings. This often leads to reduced performance and a lower sense of embodiment compared to the real body. Therefore, our goal is to facilitate users' adaptation to BRI. Here, we frame this problem as a sensory motor adaptation. Prior studies have shown how we adapt to novel sensory motor mappings, such as movement direction rotation. In such adaptations, it is known that precision of proprioception, a sense of body location and angle, is attenuated to suppress sensory conflict between vision and proprioception. Furthermore, actively attenuating proprioception using brain stimulation can promote sensory motor adaptation. Based on this, we hypothesize that proprioceptive attenuation can facilitate adaptation to BRI in virtual reality. Our previous studies have already applied proprioceptive attenuation in VR applications. We used vibration or electrical stimulation on tendons, which contain proprioceptive receptors, to suppress proprioception and induce visual-dependent perception. These studies have reported that it can make virtual hand shifts less noticeable and expand the unnoticeable range of illusory manipulation like hand redirection. However, it was limited to reducing the noticeability of illusory manipulation, and no studies have explored its effects on overt manipulation, such as BRI. We propose using proprioceptive attenuation as a method to facilitate adaptation to BRI. Where there is a mismatch between vision and proprioception because of BRI, we aim to enhance usability and control over visual virtual hands by attenuating proprioception. As a means of attenuating proprioception, we adopt noisy tendon electrical stimulation. Our previous research proposed this technique, reporting that it is easy to implement with low cost and low user load. Stimulation methods followed the previous study. Using a Gaussian white noise current, we stimulate tendons of the biceps and triceps brachii muscles to attenuate proprioception about hand positions. Our previous research suggests that the effects of n-TES vary between individuals. To address this, we developed a pointing task without seeing virtual hands to measure proprioceptive precision and propose using this to optimize stimulation levels of n-TES. A pilot study with 19 participants confirmed that this method can effectively adjust stimulation levels. From this slide, I will explain the user study that examined the effects of our proposed n-TES on the usability of BRI. In the user study, all participants went through the proprioceptive precision test described in the previous slides first, then they did a series of reaching tasks using the optimized level of n-TES in some conditions. In the reaching task to measure performance and subjective scores, we adopted go-go interaction as a classic example of BRI. As you can see in this video, go-go interaction extends virtual hands through nonlinear gain and enables users to reach beyond the real world. The purpose of the user study was first to confirm the negative effects of using go-go interaction as the problem we solve, and then to investigate the effects of our proposed method on the usability of go-go interaction. To this end, we chose a within participants design with two factors, which are with or without n-TES and with or without go-go interaction. Our hypotheses are that due to the difficulty and adaptation to BRI, performance and subjective scores will be worse with the use of go-go interaction than with real aligned hand, and those negative effects of go-go interaction will be mitigated by our proposed n-TES method. As for the procedure for the reaching task, all participants went through the reaching task and questionnaire about it for 4 conditions, with and without n-TES, with and without go-go interaction. As you can see in the video, participants reached randomly appearing targets with virtual hands. Here, we refer to the condition that uses go-go interaction as the go-go condition, and the condition without go-go interaction as the align condition. The align condition uses a hand position corresponding to the real hand's position. Though virtual hands move differently between go-go and align conditions, we position the targets so that they can be reached with the same real hand positions in both conditions. This enabled comparisons of reaching performance between go-go and align conditions. From this slide, I will present the results of the user study. These behavior measures are shown for both align and go-go conditions. The light color indicates control conditions without n-TES, while the dark color indicates conditions with n-TES. As for the effect of go-go interaction, reaching time increased and reaching smoothness decreased, indicated by a higher normalized jerk score. These results indicate lower performance with go-go interaction, supporting hypothesis 1. Also, the time averaged reaching error and the percentage time of maximum velocity decreased. This might be due to increased searching movements near the targets. As for the effect of n-TES, though most measures showed no significant effect, n-TES led to a higher time averaged reaching error, but only in the go-go condition. This may be due to reduced searching movements near targets or less smooth reaching motions, but further research is needed to clarify the specific effects of n-TES. These are the results of subjective measures. Due to the use of go-go interaction, task load increased and ownership and control scores of the sense of embodiment decreased. These results support hypothesis 1. As for the effect of n-TES, the subjective score of the sense of agency, indicated by the score of control, increased in the go-go condition. This partially supports hypothesis 2, though no significant effects were observed in other metrics. This is the summary of the results. First, the negative effects of using go-go interactions were revealed, as indicated by decreased performance and sense of embodiment and increased task load. On the other hand, there was no effect of the proposed method on performance or subjective task load except for an increase in the subjective sense of agency during the use of the go-go interaction. Overall, the effects of n-TES were limited and hypothesis 2 was not fully supported. Here are some possible explanations for the limited effects of n-TES in this study. First, the within-participant design may have caused habituation effects, reducing the impact of n-TES. Second, the proprioceptive attenuation by n-TES in this study might be inadequate because of discomfort or stochastic resonance. And thirdly, though we try to design the reaching task equal for all conditions, due to less target visibility or smaller target area in go-go condition, it might be more difficult than in align condition. This might lead to difficulty in adaptation itself. Future work should explore other types of BRI, as this study focused solely on go-go interaction. For example, in addition to detailed investigations of how the effect varies with the direction of movement, it might be fruitful to study possible effects on control over replicated body parts or how and where to attenuate proprioception for body part replacement. Also, even if the proprioceptive attenuation can be used for BRI adaptation, considering the need to do precise tasks with BRI, it might be meaningful to consider weakening proprioceptive attenuation gradually after some adaptation is achieved. To conclude, here is a summary of my presentation. Thank you for listening.